Hello everyone. In today's video, we will try to understand the equations of uniformly accelerated motion using Python. Now, these three equations describe the motion of a body undergoing uniform acceleration, which means the velocity increases constantly with time. Now, in these three equations, we have u as the initial velocity, v is the final velocity, a is the acceleration, t is the time, and s is the distance covered. Let's try to see how we can use Python for understanding such physical scenarios. Please note that this is not an in-depth Python tutorial. I will not be explaining the coding concepts involved in detail. On the way, I will explain some basic concepts here and there, but again, I will not dive deeper into it. I would urge you to check out other tutorials and videos to understand what's going on with the coding if you have not yet learned Python. Let's start with a basic problem. Here we have a racing car which has a uniform acceleration of 4 meters per second square. Now the question is, what distance will it cover in 10 seconds from the start? So the information that is given to us is the initial velocity is 0 since it's starting from the rest, and in time taken, which is 10 seconds, and the acceleration 4 meters per second square. So we have to calculate the distance it covers. We have these four variables. We can use the second equation of motion, which is s equals to ut plus half at square, to get our answer. Now we can use Python as a basic calculator to perform these operations by just directly plugging in the values, which is what I have done here. I have taken the values directly and done the calculation, which gives me 200 meters. But this is not an optimal way to write a piece of code. That's because if you want to make some changes in the values of the information that's given to us, then you would have to go and change the values in the operation itself, which is not preferred because it has the possibility of introducing some errors. So instead of that, what we will do is we will store these values in containers, which we call as variables, and then instead of manipulating the values, we will manipulate the variables, which then reduces the chances of introducing errors. And that is what I have done here. I have named the acceleration variable as a, and I have assigned the value of 4 into it. Now, of course, the unit is meter per second square, but I cannot define units in code. So this is just to keep our calculations in check and to get the correct answer. Similarly, I have defined the value of time as t, 10 seconds, and the initial velocity as u is 0 meter per second. We can then define the second equation of motion again, but now using variables, which is what we have done here. So running the operation again, we can see that we get the correct answer again. Here what we have done is, first on the right hand side of the equation, we have calculated the value of distance and then stored it in a variable called s, after which we are printing. Now the advantage of using this method is that if I just go back and change some value, let's say I want to check what would happen if the initial velocity was 10 meters per second, then just by changing the initial velocity and then rerunning the calculations, I can get a new answer instead of going back to the operation itself to change the answers. So this is a convenient way of using variables. Another advantage of using variables is apparent in the second problem here. Here we have a scooter moving at the speed of 10 km per hour and it's stopping by applying brakes, which is producing a uniform acceleration of negative 0.5 meter per second square. Now the question is, how much distance will it cover by the time the scooter comes to a stop? Now we can't just directly go ahead and perform the same calculations because the unit of speed and acceleration is different here. So we have to convert the units. Now if you are using just the Python as a calculator directly plugging in the values, then you would have to change the unit of speed from kilometer per hour to meter per second in the calculation itself, which is again very inconvenient and could produce some errors. So instead of that, while we are defining the variables, we can change the calculations directly, and that is what I have done here. So I am defining the u equals to 10 now. This is in kilometers per hour, but then I would go ahead and then change it to meter per second by multiplying by 1000 and dividing by 3600, and then the final velocity is 0 because the scooter is coming to a stop, and I'm defining a as negative 0.5 meter per second square. So since we have this information, we can see that we can use the third equation of motion here to get the distance. So solving for s, we get this expression here, and then we can again define this equation here to get the correct answer, which then gives us this distance covered as 7.71 meters. Now let's go further and look at some plots to get a better understanding about these equations and to see how we can use Python with physics even more. So here I have imported two packages for the same task. Now packages in Python or any other language are bundles of code that is written by someone else So it's very similar to how you would buy Maggi masala and then use it for your own cooking. You did not make the masala from scratch. Someone else has made it for you and you have used it for your own purpose. Similarly, these packages are written by someone else and now I am using it for my own purpose. So the two packages that I have imported here are NumPy and Matplotlib. So what importing does is it's taking the code from my storage device to my RAM so that I can access it through my code directly. So NumPy is a mathematical Python library or a package which helps in mathematical calculations in Python, and Matplotlib is a library for plotting. So I am naming the NumPy package as NP so that instead of calling NumPy again and again, I can just call NP. And similarly, I have named the Matplotlib, specifically the PyPlot package, as PLT. Let's look at the first problem of the racing car again and try to understand it through plots now. So here I am defining the variables of A and 0 again, but now instead of taking a single t value, I am taking a range or a list of t values starting from 0 seconds to 10 seconds, and between 0 and 10 seconds I am taking 100 such values. So the function that I am using is linspace of NumPy, which basically takes the starting value, the final value, and the number of values between those two start and final values, and then divides that range equally in those numbers, and then gives me back a list or a NumPy array of such values. Then I have defined two empty lists for storing the distance values and the velocity values. Now since there are multiple time values, I don't want to perform the same operation again and again manually. So instead of that, I am using a loop. Specifically, I am using the for loop. So this loop will go through each and every single time value here. The t variable here will assume the value of each time value in the array here, and then the operation will be performed in that presumed time value. So here I have again defined the equation for the distance, and then as the time value increases, the calculation will be done on each updated time value and stored in S, which will then be appended to the list that I have defined before. Similarly, I have calculated the velocity values here. Let's use the Matplotlib package for making the plots. So here I have the plots of distance on the y-axis versus time. So we can see that distance varies with time by a parabolic function here, and that's because if you look back at the equation here, S is proportional to t squared here, and so this is basically a quadratic function here. The next plot that we could look into is the velocity value versus time here, and we can see this increasing linearly in equal intervals with equal intervals of time. So that is a definition of uniform acceleration, because velocity is not varying with time but just increasing linearly. One more piece of information that you would get from velocity versus time or speed versus time is that if you get the slope of this line, then that would be the acceleration, because you are dividing speed by time to get the acceleration. And since the slope is constant everywhere on this curve, this gives us the information that the acceleration is constant throughout the motion, which is what uniform acceleration is. Now let's try to understand this plot here, which is again speed versus time, but we have a slightly different motion here. For the first 4 seconds, the body attains a speed from 0 to 6 meters per second, then stays constant at 6 meters per second for the next 6 seconds, and then decreases to 0 for the next 6 seconds. So what information can we get out of such a plot? Well, for the first half here, from 0 to 4 seconds, if we get the slope of this line, then again we'll get the acceleration, which is what we can manually do it here. So let's take this plot, which is 6 meters per second, and this point here, which is 0. So if we subtract 6 minus 0 and then divide it by the time values, corresponding time values, so here we have 4 seconds and here we have 0, so that would give us 1.5 meters per second square. So that's the acceleration during this half here. Again, it stays constant here. So if you take the slope of this line here, so you would have to minus 6, so that would give you 0, and so the acceleration is basically 0 here, and which is why velocity stays constant with time. And then if you take the slope of this line, you will get a negative acceleration since the speed is decreasing, which means the acceleration is retarding. One more piece of information that you could get from this plot is that if you calculate the area under each curve, then that would give you the distance that the body covers. That's because if you just check this triangle here, when you calculate the area under the curve, you are multiplying speed with time, and when you do that, you get the distance. Now that we have covered some basic calculations and plotting, Let's look at a very special case of this kind of motion, which is a freely falling body. If we consider y-axis to be positive upwards, then the acceleration of a freely falling body would be downwards, and the magnitude would be equal to 9.8 meter per second square, which is the acceleration due to gravity for Earth. And since the height attained by this body would most probably be incomparable with the radius of the Earth, we can consider the acceleration to be constant throughout the motion, which is why A will be minus 9.8 meter per second square. Let's look at the equations of motion again. Here we are defining A as minus g, where g is 9.8 meter per second square, and replacing A by minus g in these equations give us these three equations. Let's just look at a very simple problem to see how we can understand the motion using these three equations. So the problem here is that a ball is thrown up at a speed of 4 meter per second, and now we have to find the maximum height reached by that ball. So let's see what information we have. Firstly, we have the u equals to 4 meter per second, which is the initial velocity. The final velocity would be 0 because when we are talking about a maximum height reached, the ball would stop there for a few seconds and then would fall down. So at that instant, the final velocity would be 0. And since acceleration is again due to the Earth, g would be 9.8, but then the acceleration experienced by the ball would be minus g. If we look at these variables, we can see that we can use the third equation of motion here, and solving for h, we get this expression here. Now, if you are worried about the negative sign in the denominator here and are wondering what would mean by negative height, please note that the final velocity here is lesser than the initial velocity, which would mean that the numerator would become negative, and so the negative signs would cancel, and finally we would get positive height. Typing out the equation of motion here, we get the value of h, which is 0.81 meters. Now let's analyze the motion of the ball as it goes up and then comes back down. And for that, I have done some slight modifications to the equations by including the initial height as well. For the calculations, I have defined two functions here for getting the height and the velocity. Now, functions in Python or in any other language are blocks of code that I want to repeat multiple times throughout my main code. Since I don't want to rewrite the same piece of code again and again, I would just call this function by passing some initial parameters, and this block of code would do the calculations for me and then pass it back to me. So here in the getHeight function, I'm passing the initial height, the initial velocity, the acceleration, and the time value, a particular time instant, and then calculating the height here. Since I want the height value back, I am returning this height, h variable here. Similarly, I am defining the getVelocity function by passing the initial velocity, acceleration, and time, and then performing this calculation which is from the first equation of motion and returning the v value here. Similar to the first plotting scenario, I have again defined these initial values here, and then the time values array, which is from 0 to 2 seconds now, and again with 100 values in between for a much finer calculation. And I'm defining height values and vel values, which are two empty arrays for containing the values of height and velocity. Again, I'm using a for loop to go through each time value to make the same calculations. But here, since I don't want the ball to keep on falling even after crossing the ground, I have introduced an if condition to check when the ball is lower than the initial height. If that's so, then set the height to be the initial height and the velocity to be 0. So instead of going through that ground, it would just stay constantly with time. And then I have updated the list by appending the values here. Let's plot them now. So the height versus time plot gives us a nice curve. Please note that this is not 2D motion but 1D motion, since this is distance versus time. We can see that the ball goes up and reaches the maximum height, which is what we had calculated before also, so 0.81 meters, and then stays there for some time and comes back down and falls to the ground. Since I had introduced that if condition of setting the height to be equal to initial height, we have this straight line after it reaches the ground. The velocity versus time plot gives us an idea about how the velocity changes with time. It first starts out with 4 meters per second, then when the ball reaches the maximum height, it becomes 0, to which it again goes back to minus 4 meters per second, and then suddenly goes back to 0 since it reaches the ground now. Now I have been using for loops for these calculations, but I don't really need to. I can just use NumPy's functionality to make the code shorter. So note that when I had defined a time values array, I had used a NumPy's linspace function, which makes the time values list a default NumPy array. So here, instead of going through the time values repeatedly, I can just pass the entire array to the function. The function would do the calculations for me for each and every single time values in the array and then pass back an array instead of just a single value. So that's how I have calculated the height values again, but instead of for loop, just using numpy's functionality and the velocity values. Now, to implement the if condition above, I am using a slightly advanced concept which is called masking. So now again, as I said before, this is not an in-depth Python tutorial, so please go ahead and check other tutorials for understanding this concept. But in brief, what's happening here is, on the right hand side, I have defined a condition, which is if the values of the height in the array is lesser than the initial height, then that would return true, and which are not, that would be false. So this array of true and false values I am storing in the mask variable, and then using this mask variable, I am again checking the height values and setting those true values to be the initial height, and for the velocity values I am setting it to be 0. So this is basically a shorter way of writing and a better way of writing that if condition. We can again make the same plots again to verify our calculations in its modified coded form, and as we can see, we do get the same plots back. Before ending this video, let's look at how the energy changes with the motion. So here I have defined a mass to be 1 kilogram, and then we can define the potential energy values as mass times g times height values. So again, since I had defined the height values to be a numpy array, this calculation would be done for each and every single value, and that would make the potential energy values as a numpy array. Similarly, I had the kinetic energy values, which is half mv square, and then I'm adding the potential energy values and kinetic energy to be the total energy. Let's plot the energies values versus time to see how they change with the motion. So we can see here that as the motion starts, that means as the ball starts to go up, the kinetic energy is at its highest. Then when it reaches the maximum height, it becomes 0, since the ball stops at that point. After which, as it comes back down, again the kinetic energy increases. Now the opposite happens for the potential energy, which is that it starts out with 0, and then as it approaches the maximum height, it increases, and then it's the highest when the height is the highest, and then again starts decreasing as the ball starts to fall down. Note here that throughout the motion, the total energy is constant with time here, which is why the green line is basically a constant line here. This is basically the conservation of energy, and when the ball has no more motion, all the energies just fall down to 0. I hope you enjoyed watching this video. In the next video, let's try to make this motion more realistic by adding bounces and trying to study the physics of such a motion. If you like this video, please like and comment down below, and share it with your friends and family, and of course subscribe to the channel. Thank you, stay curious.